Any questions?
I do have on the homework questions. Number 17. It's a storage room about 72 meters in diameter. As a 20.
All right, sorry, you're on chapter 20, chapter 20. Problem which one?
17.
That's that one.
17, okay. What was read the problem again?
It was the one sphere storage room about 17 meters in diameter at the Stanford Linear Accelerator.
Okay.
My general question was, where did they get the 3 times 10 to the 8th? I don't know if you have the answers.
I do not have the answers here. Let's see, wait. Storage ring, 72 meters in diameter. At slack has 20 ampere circulating beam of electrons moving at nearly the speed of light. How many electrons are in the beam? All right. Well, why don't we just sort of walk through it? So it's asking for how many electrons are in the beam. We're given current, 20 amperes. And what's current?
It's charge over a point at a given time.
Okay. Which we generally write as delta Q over delta T. And I know that they are traveling near the speed of light. And so the speed is approximately 3 times 10 to the 8 meters per second. Was that?
That was my question.
Okay.
Where'd they get that from?
Speed of light. It's slightly less than that. It is an exact value, but that works for most things, so we get to relativity at the end. All right, I'm gonna put a pause right here because I don't have the quizzes with me because I'm unstuck in time. Slaughterhouse-5 reference.
I had a bunch of questions. I don't know.
Yeah, I'll come back. Oh. All right, Ethan, I understand you have questions.
So, some of them are like minor, but some of them are like cool problems. But so for 17, what is this? I think delta T equals C over V.
Delta T equals C over,
Or is that a V?
I don't have the solution sitting in front of me.
Yeah, it says delta T over C over V.
Oh, the circumference. It's distance. Basically, distance is speed times time.
Yeah.
We assume that there's no change in speed. There's obviously acceleration because it's changing direction, but there's no change in speed. And so distance equals speed times time, or speed equals, and they're using capital C for the circumference. It's how long it takes to go all the way. Basically, the distance it's traveling is the circumference of the ring.
Now, there's this weird notation that he uses too. It's like D semicolon D.
D, semicolon D.
If there's a pi in front of them.
Yeah,
For
there's
C.
a pi D semicolon D.
All right. I couldn't find my notebook, so I can't look at the solutions here. So I know that if that's the circumference over time, circumference is 2 pi r or pi times the diameter, since they gave us the diameter. Now, semicolon d, I'd have to see it to pull a context from that.
It says, I think it's saying C equals pi over D and then semicolon D equals 72 meters.
Oh, okay.
Oh, okay. This is.
Is that your question for this one?
For the, yeah.
Okay.
And then for 22, part C, where why is the voltage to whatever appliance is being used reduced by this amount? What is the effect on the appliance? I don't really understand the question or the answer.
All right, find the voltage drop. In an extension cord it gives you resistance, it gives you current, so I times R. The cheaper cord uses thinner wire, it has a resistance of 0.3 ohms. So thinner wire, it has a greater resistance. And the voltage drop in it with 5 amps flowing, so that's again I times R. Why is the voltage to whatever appliance is being reduced by this amount? What is the effect on the appliance? All right, so to me, the question is asking why, I mean, what does it mean for there to be a voltage drop? And it's, in essence, it's a loss of energy. Now, voltage is related to electric potential. So we have a loss of energy, which means that it's going to be a slowing down. So delta U is equal to Q delta V. So when you have this voltage drop because of a charge going through it, there is a loss of energy.
Also, it says voltage drop, but the voltage goes up from A to B.
Why is the voltage to whatever appliance being used reduced by this amount? So the first one, wait, you're saying in B?
Or, because A is, the answer is 0.3 volts, and B, the answer is 1.5 volts.
So there's a bigger drop in the second one.
It's dropping by that 1.5 volts.
Oh,
Oh, when it
okay.
says V equals IR, that's delta V, right?
Yeah, yeah, okay. Some books are really picky about that and some aren't.
So we're solving for how much it's dropping by, not the actual, like, not the voltage of it.
No, it is asking for voltage of. There's a bigger voltage, so are you looking at, there's a bigger voltage?
Yeah.
Well, as you're going with the current, so as I go with the current, technically, the change in voltage would, first one would be negative 0.3, is that it?
Yeah.
And for the second one, delta V is negative 1.5. So there is an increase in the voltage drop or a decrease in the voltage, depends on how you want to look at it. To me, it's more of a semantics argument.
And then what is the effect on the appliance? If there's a greater voltage drop, that means it would have less power?
Not necessarily, I mean, you're plugged into an outlet. What's a device that requires, sometimes the bigger the voltage drop, the better?
A fridge?
Probably not a fridge, on the other end of the cooking spectrum.
Microwave?
Not microwave,
Oven.
or toaster. I mean, that, light bulbs also, incandescent light bulbs. Because that loss of energy goes into, in the case of a toaster, a lot of heat, and there's a glowing too. In the case of light bulbs, heat and light. The heat is wasted unless you're using an easy bake oven, and the light is, well, the purpose for having a bulb. Presumably, I don't know what your thing is.
So basically you're saying that if the voltage drop is increased, it's gonna have less energy.
Less energy in the wire, more energy lost, and that energy lost is sometimes supplies us with heat, sometimes it supplies us with light, sometimes it's just a loss and it melts the insulation of the wires and your house burns down.
So it's gonna lose energy as it moves across the wire?
Yes.
Okay.
It's gonna lose energy as it goes across the wire. The lower the voltage drop, the more energy is lost. which
The
means-
lower the voltage drop, well, is that lower? Are you considering that lower?
Yeah,
Okay, the lower the energy. Semantics here. The lower the change in potential,
the lower the change in potential energy,
then the greater loss.
the greater loss. And a greater loss means that whatever appliance is being used is gonna have more heat or more light.
Yes.
Okay.
If it's too much heat, it melts, catches fire.
Okay.
I have a question about the next one after this, number 26.
All right.
Yeah, I'm done with this question.
Okay, 26, we have a 0.1 millimeter diameter tungsten filament light bulb. It has a resistance and temperature, how long should it be? Okay, this question just how to do it.
Well, my question is, where's the 5.6 times 10 to the negative 8? Because they get pi.
That's probably the resistivity of tungsten at 20 degrees,
Okay.
and presumably there's a table in here.
That tells you that.
I did not go back far enough, there we go. Resistivities of various materials at 20 degrees Celsius, page 777.
Okay. But that's just the 4 tungsten.
Yeah,
that's
presumably, just doing a quick scan for tungsten, 5.6 times 10 to the negative 8th ohm meters.
That's where we plug in for row.
Yes.
Okay.
And I say 777, at least in my version of the textbook. I don't know what it is in yours.
I also have a question regarding 27.
I have one on 26.
Oh, what's the other one on 26?
So we start with R equals rho L over A. How does
Yep.
that become L equals pi R, R squared over rho?
So resistance, rho L over A, as you just said. We're trying to find the length, so solve for length. So L equals R A over rho. The area, assuming that the wire is cylindrical, so that's R pi little r squared over rho, and they give us the diameter.
Yeah. Okay, so that's just the pi and the R squared of the area.
Yes.
Okay.
Other questions from 26? Right, Ibrahim, you had 27?
I think I figured it out, just looking at it again.
Okay.
But can you do 36, because there's like, what's confusing me is the same 1 plus AC delta T. That's the early, like that, like in the solving of it, that stuff is.
Yeah, all right, so I didn't cover the temperature relationship to resistance, but I wanted you at least to have some exposure to it.
Oh, so it's not gonna be on the quiz?
No, it won't be. But there is a formula dealing with resistivity that resistivity equals, and I don't even have it down in my head, rho sub naught 1 plus alpha delta T. And so this would be the resistivity at presumably 20 degrees Celsius. This is the change in temperature from 20 degrees Celsius, and alpha is a material specific constant, which you would look up for. Either it's given to you or you'd have to find the table where that information is.
Is 20 degrees Celsius for rho sub naught pretty standard?
20 degrees Celsius?
Yeah.
Yeah. That is roughly 70 degrees Fahrenheit.
So it's like room temperature.
Yeah, ish. The quick conversion for Celsius to degrees Celsius, degrees Fahrenheit is double it net 30. That's the quick and dirty. That'll get you in the ballpark.
So for 51, when it comes down to the conversion of, or to find out how much does it cost, so they found out that the electrical energy is 7.2 times 10 to the 4th joules, and so then they do this 9.0 cents over kilowatts per hour.
It's kilowatt hours.
Kilowatt hours times 1 kilowatt hour over 3.6 times 10 to the 6th joules. So how does that like equate to getting these cents? Or can we just be, can we use cents as if it's just another, just another unit? And
Yes,
just, like,
absolutely.
Cross it out?
At the appropriate place.
Yeah.
So you're asking for how much it costs, so probably cents is not getting canceled out in the second part of that.
Yeah. So the joules and the kilowatt hours, that's getting canceled.
Kilowatt hour is just a unit of energy.
Okay.
Because a watt is defined as a joule per second. And so a joule is a watt second. And so some time, some power, so a power unit times a time unit is an energy unit. Ethan?
On that same question, that P equals ET, is that power equals energy over time?
Yeah, basically, that's the unit version of it, but power is the rate at which energy is being used or produced, depending upon which type of energy you're talking about, but delta E over delta T. Where that E is energy, not electric field.
On 77, eventually you calculate the percent loss, but it looks like you just take the second value and divide it by the first value instead of doing final minus initial divided by final. Or divided
Yeah, if
by-
you're doing final minus initial, that's a change, and then you're comparing it to something. Percent loss, it's generally would be the loss divided by the original amount.
Yeah.
Just like we've got, we had 12 people in here, if one more person showed up, what was the percent increase? Well, it would be one person divided by what we started with, not what we ended with.
Okay, I see.
So, on number 80, I get the first part of it, or the first part of the solution,
Right?
but then it says, so that current sub naught equals root 2 current sub RMS, I think that's what
Yep.
it's, equals root 2 times, like, why are we multiplying it by root 2?
Because it's the RMS value. All right, so we'll get into this in more detail in a later chapter. However, again, this was to expose it to you now, and then later on, it presumably will make more sense. But when we're dealing with alternating current, and that the voltage is oscillating back and forth like a sine wave or a cosine wave, and so is the current, and charge, various things. So if I have we'll just take current for example. If this is current first time, flowing across some simple circuit. If I wanted to figure out, so that means that the current that's flowing out of our outlets here, it is flowing one way and then it flows back and then it flows, so the current's just moving back and forth. Because ultimately to run our equipment, you just need current moving, changing its velocity. So the current oscillating back and forth. Now, if at some point the current is zero, and other points it's a peak value, the question is, what value do we use? Well, we use an average value. The average value, well, if I average this, it goes on forever. What would be the average of current for something that's oscillating back and forth?
Current squared.
No, what is the average for current?
No.
I haven't gotten RMS yet. I'm getting to a reason why we use RMS. Yeah, I have just as much above it as I do below it. My average would be zero, which doesn't make any sense in terms of manipulation. So in order to figure out the average value, they use what's called a root mean square. The first thing you do, so root mean square, or RMS, is you sort of do it in reverse order. You square it. So the squared value, let's see if this works. Yeah, the squared value basically is going to look something like that. So you square it first, then you take the average of that, and then you take the square root. And when you do that, whatever this peak value is here, so I peak, the RMS value, so the peak value is equal to the RMS value times the square root of 2.
And the RMS stands for
Root mean square,
root mean squared. Okay.
which is basically sort of the reverse of what you actually do. You first square it, then you take the mean, then you take the square root. But it's a method of finding an average that is more meaningful, at least in this case.
I have one question about 77, which is the one before that. For part B, the equation for the answer is P equals I squared R.
Yep.
Why do we square that I?
All right. You have a question about why the P equals IV?
P equals I squared R.
Oh, no, but, so why don't we start with power? It's gonna be a pseudo derivation.